So, another look at the future of mankind, and this is the second phase of space colonization. The first phase is just colonizing our own solar system, and that is going to give us it'll give us resources for hundreds of thousands of trillions of humans. But of course, once you've done that, and then you say, what next? You realize that, it's again like you're in Zanzibar and you're looking at the African mainland and you've colonized our solar system, and then you're looking around and you're seeing the rest of the galaxy, which are like many more different solar systems. And you kind of ask yourself, is this it? Are we just going to stop at our own solar system? Why not go and also colonize uh, Alpha Centauri, which is essentially a system of three stars? Lots of mass there, which can be converted to space habitations. And the question is, it's very far. It's about over 4 light years away. And then the question arises, would it be possible, given our present knowledge of physics and based on our present knowledge of the laws of physics, is it possible to actually build an interstellar colonizing vessel? So I'm going to describe the design of a vessel. And it's important to understand that these are all consistent with what we know of physics now. There is nothing like, oh, that someday we're going to do like wormholes and we're going to travel faster than light, blah, blah, blah. No, none of that. This is proper science. You don't say those things if you're a proper scientist. Love to be proven wrong, but I don't think it's going to happen. Okay, so what is the design for this colonizing vessel? Well, essentially, it is based on the design for a space habitation with an engine added to it. Okay, and there are some design goals for it. The first goal is that the population of ICV flotilla, so there'll actually be 10 of them. Okay? So there will be 10 of them in a flotilla. It won't be just one spaceship by itself. That's like kind of risky. You'll get bored. You want a variety of landscapes. One ICV will be like a tropical island inside of it. The other one will be like a alpine mountain ranges, and another one could be just a city, a major city. So just a variety. That's one thing. The second thing, why you would rather have a flotilla of 10 ICVs rather than one ICV is that it reduces the risk. If there's some damage happens to one ICV, then the remaining ICVs can help repair it, or they can evacuate the inhabitants. So this design for the flotilla is based on 10 ICVs in the flotilla. And the total population of the flotilla will be 12,500. And so that's a design goal. And the nuclear fuel needed for the flotilla should not be more than 1.5 times the average global production of uranium-238 from 2013 to 2022. So I just have to, when you're designing these things, you have to, your constraint is obviously fuel, and you're going to have a design with nuclear fuel, and you just can't say that, oh, I'm going to use this fantastic amount of fuel, so let's just keep it within 1.5 times the global production of uranium-238. Uranium-238 is actually quite a commonly occurring metal, and in fact, thorium is even more common. So let's look at, so it's essentially a space habitation with the engine attached. And then, now what about this engine? So the engine, ejects something, law of conservation of linear momentum. You got to throw out something at a very high speed to get some reaction force, action and reaction force to be able to get to a high speed. So let's say chemical rockets and all just won't work, because the speed at which they eject mass is just too low. So what we're going to look at is we're going to look at electromagnetic railguns as the for the engine, for the rocket, and it's just going to first there's a calculation of how much electromagnetic railguns actually, what acceleration they achieve. And there is one experimental electromagnetic railguns designed by BAE Systems, unfortunately a defense contractor, which of course, I'm no fan of defense contractors. But this was the data I could find, so here they are. And it's 114,920 meters per second squared. That seems to be around what they were able to achieve. The acceleration, or it's about 12,000 G. That may seem very high, but actually it's apparently like these railguns can achieve accelerations of 100,000 to 200,000 Gs. Okay, so then the railgun for this ICV is going to be 20 kilometers long. It may seem a very large rocket, but 20 kilometers is nothing. think of just a few hundred years ago, what did we have? We had canoes, and now we have cruise ships. Just compare the size of a canoe and a cruise ship, and you can sort of understand why we should not, based on our current experiences, believe that, oh, this is what is feasible and this is not. Okay. So just a 20-kilometer railgun has an acceleration of 114,000 meters per second square. So the velocity of the eject is 67.8 kilometers per second. And that is very much larger than what you would get from a chemical rocket. So that's the point of having an electromagnetic railgun. Okay, the mass that you shoot out can be at a much higher velocity. And then we apply the Tsiolkovsky rocket equation, which basically tells you if you start with a certain mass and you eject a certain percentage, a certain fraction of it, what is the velocity, the change in velocity of the remaining mass, the remaining rocket, which has ejected that mass. And that turns out to be, if you're ejecting the mass at a speed of 67.8, then the remaining rocket would have a speed of 15.13, assuming that 20% of the mass was ejected.